Chapter 12 Relationships Without Boundaries. Celebrity physicists and university textbooks would have you believe that spacetime is a physically real substance. Even worse, some often claim that ontological spacetime is a requirement of general relativity. There is zero evidence for this claim, with the only support coming from circular reasoning and ad hoc assumptions. The substantivalist position originated in the 17th century. While many philosophers have proposed similar positions throughout history, the era of Newtonian physics led to a shift in perspective. Newton viewed spacetime as a container for objects. He believed a background was necessary to serve as a relational reference for the motion of objects. His famous bucket experiment involved spinning a bucket of water tethered by a rope. While at rest, the water in the bucket sits flat, but while spinning, the surface of the water becomes concave. Newton believed this demonstrated that spacetime must be a fixed, immutable background that exists independently of mass and energy. Substantivalism is still alive today, though the idea is quite a bit different from Newton's perspective. Everything changed again after Einstein introduced relativity. The debate between relationalism and substantivalism intensified in many ways, with several complex arguments and proposals being presented on both sides. For the most part, the topic has gone silent, with debates falling outside of the mainstream and out of the public view. Substantivalism has gained considerable ground in contemporary physics, though the reasons for this dominance remains unclear. One contributing factor is that the practical convenience of substantivalist language when discussing physical absolute reference frame. Additionally, many physicists may not be aware of relationalist alternatives. While this observation is admittedly anecdotal, most people with an introductory knowledge of general relativity seem to interpret the theory as requiring spacetime to exist as a genuine physical entity. The widespread use of the substantivalist terminology in physics, education, and research has only reinforced this interpretation. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. Basically, anyone trying to explain general relativity. The whole argument. General relativity adopts several mathematical procedures and proposals. The most commonly discussed idea is that of general covariance, which is arguably the engine of general relativity. General covariance is a requirement that the equations of all physical laws have the same form in all coordinate systems. All equations must be written using tensors that transform covariantly under smooth coordinate transformations. A theory is generally covariant if every equation describing its laws look the same in all frames of reference, i.e., the equations are relations between general tensors. Diffeomorphism invariance refers to the arbitrary nature of spacetime. It is very similar to general covariance, but also different in subtle ways. If general covariance is about the arbitrariness of labeling spacetime, Diffeomorphism invariance refers to the arbitrariness of position, the idea that points in space have no absolute identity or unique characteristic. Consider two stars separated by a region of empty space, which we designate as the whole. Suppose we have a solution to Einstein's field equations that describes the gravitational field produced by these stars, including in the empty region between them. Now apply a diffeomorphism that alters the metric only within the whole, while leaving the region outside unchanged. This transformation yields a new solution that differs in the whole but matches the original elsewhere. Both solutions satisfy the field equations and agree on all observable data outside of the whole. If one holds that spacetime points have intrinsic identity, then these two solutions represent physically distinct realities, since they differ inside the whole but are identical elsewhere. This would imply that the field equations do not fully determine the metric, leading to indeterminism. To avoid this, one can reject the notion that spacetime possesses an identity that is independent of the fields. In this relational view, the two solutions are physically equivalent, with only the labels being different. The whole argument was first introduced by Einstein. It has been refined and adjusted through the years, but as a formal argument, it is absolutely devastating to substantivalism. As Einstein explains in his 1916 review of general relativity,
that this requirement of general covariance, which takes away from space and time the last remnant of physical objectivity, is a natural one, will be seen from the following reflection. All our space-time verifications invariably amount to a determination of space-time coincidences. If, for example, events consisted merely in the motion of material points, then ultimately nothing would be observable but the meetings of two or more of these points. Moreover, the results of our measurings are nothing but verifications of such meetings of the material points of our measuring instruments with other material points. Coincidences between the hands of a clock and points on the clock dial, and the observed point events happening at the same place at the same time. The introduction of a system of reference serves no other purpose than to facilitate the description of the totality of such coincidences. We allot to the universe four spacetime variables x1, x2, x3, x4, in such a way that for every point event there is a corresponding system of values of the variables. To two coincident point events, there corresponds one system of values of the variables, that is, coincidence is characterized by the identity of the coordinates. If in place of the variables x1, x2, x3, x4, we introduce functions of them as a new system of coordinates, so that the systems of values are made to correspond to one another with their ambiguity, the equality of all four coordinates in the new system will also serve as an expression for the spacetime coincidence of the 2 point events. As all our physical experience can be ultimately reduced to such coincidences, there is no immediate reason for preferring certain system of coordinates to others. In other words, we arrive at the requirement of general covariance. There you go. Let me know if there's another one you want read out.
would you like to summarize it?
Sure, I can distill it down for you. In essence, he's just saying that the whole idea of general covariance is about not playing favorites with any particular coordinate system. Everything we measure is really just about these coincidences, points where things meet in space and time. And once you realize that, you realize there's no single, correct way to map out the universe. Any coordinate system that describes the same meeting points is just as valid as any other. So in short, it's just a gentle philosophical shrug at the idea that any particular frame of reference is the true mark.
This quote is one of Einstein's most philosophically important passages, and it gives a clear and compact explanation of how he resolves the whole argument and redefines physical meaning in general relativity. In this passage, Einstein is acknowledging that general covariance eliminates the idea that space and time are absolute objects. This is the philosophical foundation of general relativity. Space-time points have no identity outside the web of physical relations. Substantivalism violates diffeomorphism invariance. Therefore, only the relationalist view is compatible with general relativity. Space-time is not a substance. The vacuum is a hypothetical realm that refers directly to a region that lacks mass or energy. The vacuum cannot and does not exist as an independent object with properties of its own. The vacuum is a relational structure built from the behavior of matter and light. Geometry has no shape apart from the interactions that define it. There is no universal clock or measuring stick. There is no observer at infinity. Minkowski space, cosmic time, background geometry, the cosmological constant, or zero-point energy. The universe is not flat, closed, or open. Space-time does not expand, accelerate, contract, or dilate. Dimensions are human-created abstractions that only exist within the conceptual realm, along with other concepts like money, laws, and the number 0. Dimensions are not physical things with properties of their own. Dimensions are mathematical tools that are used to describe the properties of physical objects and events. Mass and energy are not integrals, point particles, quantum bits, or particular flavors of quantum quarks. Mass and energy are direct references to the physical universe. 1 kilogram of mass is approximately 1 over 8.6 times 10 to the 52 kilograms of the observable universe. Or not kilograms, it's just one part of the universe. They are typically discussed in terms of particles, but mass and energy are better understood as properties of fields and as systems in quantum field theory. A particle is an aberration of an infinite field, part of a series of fields that permeate all of reality. The FLRW metric assumes a co-moving coordinate system in which observers remained at fixed spatial coordinates, while the scale factor A encodes the expansion of space. The metric takes the form, and this coordinate choice imposes a specific gauge where the radial coordinate r is treated as a static label for co-moving observers, rather than a dynamical quantity. The expansion is encoded in the time-dependent scale factor A. If diffeomorphism invariance means space-time points lack genuine identity, then the FLRW metric's reliance on a preferred foliation is problematic. The FLRW model assumes a specific way of slicing spacetime into spatial surfaces of constant time, but this appears to single out a particular coordinate choice as a physically special one. When cosmologists talk about the expansion of space or the age of the universe, they're implicitly referring to this preferred cosmic time coordinate. But if space-time points don't have intrinsic identity, what justifies treating this particular temporal slicing as more than a convenient mathematical choice? The gauge incorrectly fixes the observer's position at r equals 0, ignoring the relative nature of the potential. The use of co-moving coordinates means that gravitational redshift appears to be negligible, when in fact there is an enormous amount that accumulates along the null geodesics between the emitter and observer. The assumption of homogeneity and isotropy effectively suppresses the potential gradients, which are the most important elements for determining gravitational redshift. If the vacuum is defined as the absence of mass and energy, then the relationalists win on a technicality. If diffeomorphism invariance is a gauge freedom, then it seems there is no justification for the substantivalist position in the first place. Review and closing thoughts. In previous chapters, we laid the groundwork for a new cosmological paradigm. The model was built entirely through parsimony and first principles. The reasoning is well justified. The universe cannot be homogeneous because mass density is a scale-dependent variable. Any realistic density profile creates a gravitational redshift that is proportional to the distance of light travel. And spacetime does not have properties of its own. There is no way to avoid scale-dependent gravitational redshift in a cosmological setting. The change in frequency is directly proportional to the change in potential. More importantly, potential is directly proportional to the distance of light travel. The problem in modern cosmology is one of scaling. The FLRW metric scales the gauge choice in one way, but fails to preserve the potential along the null geodesics. When deciding on gravitational redshift, you must consider the path of the photon. It is not enough to say this region here is approximately the same potential as that region over there. Gravitational potential is a relative phenomenon. The potential accumulates along the null geodesic pathway. We cannot simply compare the potential at emission point A to the potential at emission point B. We must compare the potential at emission point A to the potential of AB, which includes points A and B and everything in between.